Hi, I'm Melissa and welcome to Scopes University. Many engineers want to know what makes one oscilloscope better than another and how to tell if an oscilloscope makes high-quality measurements. This becomes even more important when you go up in bandwidth because you might be catching higher frequency noise. By looking at the data sheets, you might think that the bit characteristics of the ADC is the best tell of the quality of the oscilloscope's measurements, but it doesn't tell you the whole story. You want an oscilloscope that shows you the best representation possible of the signal that's actually occurring on your device. You don't want an oscilloscope that will inject noise and jitter into the waveform that could lead to reduced margins and failing specification. So today, let's decipher 3 different specifications and learn which ones translate into meaningful information about the quality of measurements your oscilloscope is able to make. ADC bits, system ENOB, and noise floor. The place that many people start their evaluation of an oscilloscope is with the characteristics of the scope's ADC. There are scopes now with 8, 10, and 12-bit ADCs, so what does that actually tell you about the oscilloscope? Just as the name suggests, the analog to digital converter takes your analog signal and quantizes it into digital information. So if I have an 8-bit ADC, that means that I can get 256 quantization levels. In terms we can relate to, this is the vertical resolution of the ADC. Here on screen, I've got a 1.8 volt peak-to-peak signal, which means I want to set my vertical scale such that I have about 2 volts full screen. With 256 quantization levels at this vertical setting, the best resolution I could get is 7.8 millivolts. The S-Series has a 10-bit ADC, so with the same vertical settings, I can now get 1.9 millivolts of resolution. Just like pixels on the screen, the finer the resolution, the clearer the representation will be. As we can see in the math that we just went through, 2 additional bits can potentially give you 4 times the resolution. I say potentially 4 times more resolution because there's a lot more to consider. For starters, there's no such thing as an ideal analog to digital converter. This means that just the process of quantizing that signal can induce noise and jitter. The better the ADC, the less noise will be injected. Therefore, if you want to know the applicable specs of the ADC, you want to look for the effective bits of the ADC to account for any noise added in by the analog to digital conversion. That will get you one step closer to understanding the quality of measurements made by the oscilloscope. But the ADC is just one part buried inside the oscilloscope. What about all the other stuff between your signal and the analog to digital converter? The front end of an oscilloscope consists of attenuators, preamplifiers, signal path routing, and possibly filters before it gets to the ADC. Each of these components could add noise and impact your measurement. If the front end of the oscilloscope isn't designed well, it doesn't matter how many effective bits you have on the ADC. A poorly designed front end will inject a lot of noise and a lot of jitter into the measurement, providing you with an inaccurate representation of your signal. All the noise from the front end will be injected into your signal, wasting the ADC's resolution on quantizing noise. That's why I recommend looking at the system's effective number of bits. System ENOB will account for all the parts that I discussed in the front end and the ADC and tell you the true vertical resolution achievable on your oscilloscope. Now that we know the importance of looking at the entire system, a good test of the quality of measurements the oscilloscope is able to make is to check the noise floor. Here's a quick way to measure the noise on your oscilloscope. First, let's disconnect all inputs. Remember I said we want to check multiple vertical sensitivities. Let's start with 50 millivolts per division, since that's an industry standard for measuring noise. Then we'll go to Analyze, select Histogram. We'll choose Vertical since we're looking at noise. Select the default window and turn the histogram on. You can see that this 8 GHz scope at 50 millivolts per division gives me 1.3 millivolts of noise. I also want to look at my noise results as I move position on screen. I want to make sure the noise doesn't change based on the waveform's position. If I'm comparing to another oscilloscope, I want to make sure the bandwidths match. For example, if I want to compare to a 2 GHz oscilloscope, I can apply a hardware filter to make an apples-to-apples comparison. Now, configured as a 2 GHz oscilloscope at 50 millivolts per division, I get 590 microvolts of noise. When you do this on your own, make sure to change your volts per division settings. Because we're taking the measurement on the oscilloscope itself and not depending on separated component specs provided by a vendor, we know that we're accounting for the entire system of the oscilloscope. Even though ADC bits have become a major banner spec, now you're smarter than the marketing folks. You can determine on your own which oscilloscope is going to provide you with the highest quality measurements. When you have a well-designed oscilloscope, you won't lose important details to noise. You'll have a true representation of your signal, and you don't have to worry about failing a margin spec due to induced noise and jitter. Thanks for joining me today, and if you want to see more content like this, follow us on YouTube, Facebook, and Instagram.